Okay, so are you able to see the
Yes,
slides?
sir.
Ah,
Yes, sir.
okay.
And next slide also.
Yes, sir.
Newton's method slide.
It's a splitted slide, sir, so we can have a full screen. Yes.
Huh? Oh, you're seeing split slides, huh?
Right, sir.
Okay. Okay, so last class we are looking at this we started this Newton's method for multiple variables, that is two or more variables, and then we studied the background of the Newton's method using single variable problem, that is fx versus x. Okay, so x is here, fx is here, and by using the Taylor series truncation, we obtain this equation for the delta x for single variable problem. So if you have the objective function like this, you are starting from x, x naught, then at this distance of delta x, you are likely to find the minima. Okay. So now you can extend this for two variables. Okay. So then this will become the vector of first derivatives or Jacobian matrix. Jacobian matrix is vector of first derivatives, and this will become Hessian matrix or matrix of second derivatives. Okay. So let us see how it will become. So for two variable problems, it will become like this. So this is actually delta x and delta y. Okay. Okay. So x1, y1, that is the next point, is equal to current point minus inverse of the second derivative matrix multiplied by the first derivative matrix. Okay. So this will give x naught, y naught minus delta x, delta y. Okay. Okay, so this is the Newton's method for two variable problems. We should have starting point, and then you subtract this inverse of second derivative matrix multiplied by first derivative matrix, and then you get the next point x1, y1, where the slope will be equal to 0. So for quadratic functions and for convex objective functions, the convergence is very rapid. In fact, in one iteration, you will get the solution if the objective function is quadratic and convex. Okay, then modified Newton's method. So this method will not work well with non-quadratic functions. For example, cubic function, etc. This method will not work well. So for non-quadratic functions, modified Newton method is used, which works better than the previous method. So in this modified Newton's method, we had to do a line search of the objective function along this vector. Okay. So okay, so this is the equation for the line search. So we'll see worked examples of both. That is for the, this is called basic method. This is called modified method. Okay. Okay, so this will give the parametric equation because H is there. This will give the parametric equation of the search vector. And you have to substitute this in the objective function and search along the vector. And the minima will be found along that vector. So I will do one example of each. Okay, so first is the example of the basic method. So find the minima of this quadratic objective function. That is f of xy equal to 8x squared plus 4xy plus 5y squared. So this is the quadratic objective function, and also you can see that this is convex. Okay, it will have a cup shape. Okay, the starting point x0, y0 is 10, 10. So what you have to do is that this is the equation for the next point. Okay, so first you have to find the inverse of the second derivative matrix, and then multiply it with the column vector, which is the first derivative matrix. Okay, so first let us look at this first derivative matrix. So first derivative, that is del f at x0, y0. So partial f by partial x at x0, y0, partial f by partial y at x0, y0. So you get these two equations, and you substitute 10, 10 in this equation. So this is the value of the del f vector at 10, 10. Okay, then find second derivative matrix like this. And here you have to put inverse of the second derivative matrix. And here you have to put this 200 and 140. Okay, so let us see the substitution. So x1, y1, next point where the slope will be equal to 0 is equal to first point minus inverse of Hessian matrix multiplied by del f. So if you do all the simplification, you get exact minima in one step. So you are getting exact minima in one step because it is a quadratic and also it is convex. Then minimize this non-quadratic function. Actually, this is raised to 4 and all that. Okay, minimize this non-quadratic function starting at x0, y0 equal to 2, 1 using the modified Newton method. Actually, this method is difficult to solve by hand, so it is done with help of some MATLAB or something. So first you find the first derivative vector at 2, 1. Okay, so this is the first derivative vector at 2, 1. Okay. Then you find second derivative vector at 2, 1. So these values are got. Del f at x0, y0 and h at x0, y0. Okay. So expression for the search vector for the modified Newton's method. So this is the expression for the parametric equation of the search vector. So the small h is there, which makes it parametric. So you substitute everyone. 2, 1 is the starting point. This is the parameter small h. This is the inverse of the second derivative matrix, and this is the first derivative matrix. So this is the equation, parametric equation of the search vector. Okay, or x is equal to 2 minus 3.313 into h. Y is equal to 1 minus 1.917 into h. So that is the equation of the straight line. Along with, we have to search the objective. So what you do is that in this objective function, wherever you see x, you put 2 minus 3.313h. And wherever you see y, you put 1 minus 1.917h. And after a lot of simplification, you get the value of h where minima occurs as 0.342. That is, h star is 0.342. And if you substitute this h star here, you get the value of x1, y1 as 0.8670 and 0.3444. So it has not reached the minima because a non-quadratic function you have to do many iterations. So then you have to start next iterations from this 0.8670 and 0.3444. So this is the Newton's method. Then next we look at a highly important method called Marquardt method, which is used in many algorithms. Okay, So what is Marquard's method? Marquard's method is a combination of Cauchy's steepest descent method and Newton's second derivative method. Initially, the Marquard's method will imitate the Cauchy's method, covering large distances and coming near the optimum. So in the final stages, the algorithm will imitate the Newton's method by rapidly converging to the optimum. Okay, so I already told you this. Initially, Cauchy's method is used, which will cover long distances, and in the end, you use this Newton's method to come directly to the optimum. Okay, so what is the method here? Okay, the basic equation of the Marquard method is given here. Okay. So xk, yk is the current xy point. So this is actually a second derivative matrix. Lambda is a scalar value given by the user. I is the identity matrix. Okay, I is something like this: 1, 1, 0, 0. I is identity matrix, and this del f is actually first derivative matrix at xk, yk. Okay, so this is the general equation of the Marquard method. So here lambda is a control parameter which is decided by the user. So by changing the value of lambda, we can imitate Cauchy's method or the Newton's method. So let us see how it is done. So if lambda is very small, then the above equation represents the Newton's method. So if lambda is very small, this term will vanish. Okay, so you have this inverse of the h into multiplied by this del f, and as we saw just now, then the above equation will represent the Newton's method. Okay, then okay, then if lambda is very large, the lambda into I term dominates over the H matrix. So if lambda is very large, this will become negligible. Okay, suppose you put lambda equal to 10,000. Okay, and lambda and I will become 10,000, 10,000. Okay, so and H matrix may be like say 0.8, 0.9, okay, 1, 5, etc. So when this is added to the H matrix, the effect of H matrix will become negligible. So okay, when lambda is very large, lambda into I term will dominate over the H matrix. H matrix will become negligible. So this approximates the Cauchy's method. This is not exactly Cauchy's method, but it approximates the Cauchy's method. So algorithm starts with a large value of lambda. That is, we want to imitate Cauchy's method first. It starts with large value of lambda first, which is progressively decreased in geometric steps such as lambda by 2, lambda by 4, etc. So it will gradually represents the Newton's method. So it will gradually lambda decreases, representing more and more Newton's method. So the change from Cauchy's method to Newton's method is gradual, as the value of lambda changes gradually. Okay, so now we will directly look at the worked example. So one objective function is given and starting value is given. X0, Y0 is 0, 0. Use Marquard's method to find the minimum. So first you find del f at X0, Y0. You get minus 14, minus 22. Then you find second derivative matrix at X0, Y0. So you get minus 42.1, minus 25.9, which is the Hessian matrix. So first we give large value of lambda. Okay, so it will represent the Cauchy's method. Okay, so large value of lambda is given here. So this is x naught y naught. Okay, this is x naught y naught. This is H inverse. This is I. Okay, lambda into I. This is del M. So you get next point is 0.242 and 0.297. So this is the next point. So what you can do is that you can check the objective function value at f of x1, y1. So objective function value has decreased compared to f of x naught, y naught. So we are going in the right direction. So we'll do one more iteration with a lesser value of lambda. So now lambda is 100. So next step we reduce lambda to 100 by 4. Okay, and repeat the same iterations. Now starting from this x1, y1. Okay, so next iteration, lambda is reduced to 50. So find Jacobian and Hessian matrix. So x1, y1 is equal to, so the next starting point is this. So this is the next starting point, h plus, this is lambda into I. H plus lambda into I, this is del F. Okay, so you get your next point as 2.98 and 2.05. Okay, so, okay, then what will be the next value of lambda? Next value of lambda will be 25, 50 by 2, and you repeat the same things. So this method is a popularly used method. Okay, then improvements in the Marquardt method. So in this basic Marquardt method, H is unnecessarily calculated for large value of lambdas. Okay, because as I told you, when lambda becomes big, lambda into I becomes much greater than H. So unnecessarily you are using the value of H. So according to the improved Marquardt method, what you do is that instead of using the I matrix, you use the diagonal values of the H matrix. Okay, so suppose this H matrix is 15, 20, okay, 0, 1. Okay, so this the diag of H is 15, 20, 0, 0. Okay. Okay, so that way the values, the elements of the H matrix are used here instead of becoming negligible and being ignored. Okay. So this is the improved Marquardt's method. So there's no worked example with improved Marquardt method, so that we can try later.
Sir, am I audible?
Yeah, I can hear.
So one query, what are we meaning when we say that we are actually adding the multiplication of lambda with diagonal of h? Graphically, can you explain what is happening in that particular equation?
Graphically, I don't know. See, I already told you, okay.
Because that is a second derivative matrix and we are multiplying using a lambda, which is nothing but a, it is almost as if we are telling that we are trying to minimize the rate of change and then slowly calculate the minimum. That is what is happening?
Yeah.
Okay.
So that is not the thing. Okay, so you understand this Newton's method, no? Where this is not there. Huh? If lambda is not there, then this becomes the Newton's method. Okay, so now we are going to add this lambda into I to suppress the H matrix and make it more similar to Cauchy's method. So that is the graphical explanation. As this matrix vanishes and as this I matrix becomes more important, then it represents the Cauchy's method. Okay. So that is the main logic here. Okay. So what I'm saying is that, so if lambda into, okay, so suppose that lambda becomes like 10 raised to 6 or something. So lambda into I become 10 raised to 6, 10 raised to 6, 0, 0, plus this H matrix. H matrix may be like 12, 1, 0, 2, etc. So this will become 10 raised to 6 plus 12, 1, 0, 10 raised to 6 plus 2. Okay, so this H matrix will have no effect when you give large values of lambda. Okay. So when you give large values of lambda, then it will represent this Cauchy's methods more because the second derivative matrix is gone. So that is the main logic there. Okay. So then it will do this right angle searches. Okay. That is the main explanation given in the textbook. I don't know how to graphically plot this and explain. Okay, so next we go to another method. This Powell's conjugate direction method. This Powell's conjugate direction method is also fast and accurate for quadratic functions. And there's no need for derivatives, but it requires three line searches. Okay. So let us see what is the basics of this Powell's conjugate direction method. So in this method, the user has to specify two starting points. Okay, this x1 and x2. Any two starting points. Okay, here this x raised to 1 actually means x1, y1. X raised to 2 means actually x2, y2. Okay. Then after that, the user has to specify a search direction D. So in this particular case, the search direction D is inclined like this, say maybe 30-degree search vector. Okay. So you have to specify a search vector D by giving the I and j values. Okay, so suppose I is equal to 2, j is equal to 1. So D is equal to 2i plus 1j. So you just give the direction of the search vector. So user has to give two starting points, x1, y1, x2, y2, and to give a search direction. So from x2, you do line search of objective function like this in the direction parallel to D. And it will touch a particular contour at M2. So because there are infinite number of contours, it will always touch one contour. Okay. Then what you do is that from x1, you do another line search along the same direction D, and it will touch another contour at M2. Okay. Then according to this Powell's method, if the function is a quadratic objective function, then the minima will lie along the line joining this M1 and M2. Okay. So you can change the search vector also. Okay. Suppose contours are like this, x1 is, x2 is here, x1 is here. So suppose you change the search vector like this, D, okay? Okay, then when you search along x1, you will touch this contour. When you search along x2, you will touch another contour. Okay, okay, and the minima will lie between x1 and x2. So whatever be the search vector D, and wherever you take 2 points x1 and x2, it will bracket the minima. So this happens only to quadratic objective functions, and also they must be convex. Okay, so the global minima lies on the line joined by M1 and M2. So by conducting a line search along this direction, we can find the minima. So you need to do 3 line searches. Okay, so one is this line search. This is the first line search. That is through x1. Then this is the second line search through x2, and this is the third line search through m1 and m2. So three line searches are required. So there's no need to find first derivative, second derivative, etc. Okay. So then there's another mathematical property, that is the vector D and the vector m1, m2 are called conjugate vectors. So this vector D and this vector m1, m2 are called conjugate vector. So what is meaning of conjugate vector we'll see in the next slide. Okay, so actually this slide is just a mathematical explanation. You need not study this. It's not required for solving the problem. This is just because it is written in the textbook, I am telling you. Okay, so if an objective function can be expressed in the quadratic form, okay, so only a quadratic objective function can be exactly represented in the quadratic form. Okay, so suppose I have a quadratic function like this: x squared plus y squared plus 2xy plus y plus x plus 20 is equal to 0. Then it is possible to rearrange the objective function in this manner. Okay, with some effort you can write this objective function in this manner. Okay, that is a plus b1 b2 into xy, then half of xy into then c1 c2 c3 c4 into xy. Okay, so this is the quadratic form. Okay, so any quadratic objective function can be rearranged in this form. Okay, okay, then this vector D and this vector m1, m2 are connected by this relationship. So this C matrix will come here. So this vector m1, m2 into this C matrix into D will be equal to 0. Okay, this is called conjugate vectors. Okay, okay, so basically what I am going to say is that it is because of this property that you can find the minima along m1 and m2. So that is the only mathematics I am going to emphasize here, which is because of this property that from D you can calculate m1, m2, and then the minima will lie between m1 and m2. Okay. So one of the results of this property is that m1, m2 will pass through the minima. So this is the summary of the theory behind the Powell's method. So we are basically not very much interested in this. We'll just look at how to solve the numerical problems with the Powell's method. Okay. So find the minima of this quadratic objective function using Powell's method. So two starting points are given. x1, y1 is 0, 0, x2, y2 is 1, 0. Then the dire search vector is a 45-degree search vector. So I is equal to 1, j is equal to 1. Okay, so this is the xy plane. x1 is 0, 0. x2 is 1, 0. And search vector D is like this 1, 1. So it is 45 degree. So what you do is that through the 0, 0, you have to do a line search parallel to D. And then after that, through 1, 0, you have to do a line search parallel to D. and then you will find the 2 points. M1 here, M2 here, and then you have to do line search between M1 and M2. So minima will come somewhere here. So this is what I am showing in advance. Okay. So let us see. Okay. First is conduct a line search of the vector um, starting from 0, 0 and parallel to D. Okay. So D is equal to 1I plus 1J. So what is the parametric equation of the line starting from 0, 0? And this is 1 and this is 1. Okay. Okay. So delta x is equal to 1, delta y is equal to 1. So this is delta x, this is delta y equal to 1, this is 1. And this is x naught, y naught. So parametric equation of the search vector passing through 0, 0 and at 45 degrees is x equal to h and y equal to h. Okay. So then you have to search the objective function now by substituting this h values. So wherever you see x, you put x equal to h. Wherever you put cy, you put y equal to h. And then you do line search along that slice of objective function. You get m1 is minus 16. Sorry, minus 1 by 6, minus 1 by 6. Okay, so you can see here, okay, m1 is, okay, you did this line search, so you find m1 is minus 1 by 6, minus 1 by 6. Okay, so next, conduct a line search through x2. X2 is this. This is the search vector. Okay, so what is the equation of this search vector? Okay, so now starting point is 1, 0. Okay, and this value is 1, 1. So it is 1, 0 plus delta y is 1, delta x is 1. So delta y is 1, delta x is 1. So this is the parametric equation of this line. Okay. So you substitute that in the objective function and you find m2 is 1 by 6 minus 5 by 6. So you find m1, you find m2. Now you have to do the search between them. So what is this parametric equation? What is this parametric equation? Okay, so that we'll see in the next slide. So this we can take as starting point, this we can take as ending point. Okay, so the parametric equation of joining m1 and m2 is, this is the starting point, plus h into this is m2 minus m1. Okay, so this is the parametric equation of the line joining m1 and m2. Okay. And substitute in the objective function and we get the exact minima as lying between m1 and m2. That is minus 3 by 16, minus 1 by 8. Okay, so it is lying somewhere here. Okay. So this is the Powell's method. So you have to do the 3 line searches. Okay, so what if the function is not quadratic? In that case, many iterations are required. So now what happens is that we got the best value of the minima. Best value of the minima will lie in the middle of m1 and m2. Okay, so this final point and one of the previous points x1, y1 or x2, y2 can be used, whichever has the smaller f of xy value. Okay, so this is like this. M1 is here, M2 is here. So this is the M star. So you can take M star and one of these points for the next iterations. Okay. And then you can do the entire method, starting this as x1, y1, and this as x2, y2. Okay, we can stop now. So this method we study tomorrow, lecture is method. So tomorrow we'll also study some MATLAB toolbox. So after that, I'll give the assignment, and some of the assignment questions have to be solved with MATLAB toolbox.
Okay, sir. Okay, sir. Any,
And then we stop.
Okay, sir.
I have to take attendance. Okay.
right, sir.